Welcome again for the course of analysis of several variables, and we continue with the module 4 partial derivative and directional derivatives, and this is the last part of this chapter or this module. And in this part we are going to solve examples based on the whole chapter 4. So we have our first example here where we have given a functions f from R2 to R, which is defined by in two part, with when the point is not equal 0 0 means except origin. This is given by these expressions, and the case of at origin at 0 0 the function is 0. So we have to prove that that f is continuous at 0 0, and then we have to find the existence of the directional derivative at 0 0 for any direction of a vector v, and then conclude that f is not differentiable at 0 0. So it is continuous but not differentiable. Okay, so let's start. Okay, so first that we have to show that f is continuous at 0 0, and we are going to prove it by showing that absolute value of f of xy minus f of 0 0 is less than equal gxy, where gxy is a function of xy such that it will tends to 0 when xy tends to 0 0. So if we are able to prove that, then this is equivalent to say that limit of f of xy at 0 0 is equal f of 0 0. So that means f is continuous. Okay, so first we recall the function here from the previous slide. So we have given function is this one, and then we are going to apply this equation. So this will gives you here f of xy minus f of 0 0. So f of xy is this one, and f of 0 0 is 0. So now we are going to simplify it and so that how we can write it. So this can be written as y e to the power y and y square over x square plus 3y square. So why we are taking this one? So from and how we are taking this one? So from this part y to the power 3 we kept y square, and remaining y and e to the power y separately, and here y square plus 3y square. So now why we write it like this is because the fact that y square over x square plus 3y square. So which whatever may be the y is positive, negative. So this can be written as 1 over 3, which is less than 1. So we are using this concept. Then from that we are getting here this is less than equal y e to the power y. In fact, it is not less than equal, it is strictly less than. So it is less than y e to the power y. So now this we are taking as the function of gxy to fulfill the requirement of this one. So take gxy equal y to the power y, absolute value, and then clearly gxy is going to 0. Gxy is going to 0 as xy tends to 0 0. So therefore we fulfill the conditions, this one. So this implies that f is continuous at 0 0. Now come to the second part, where we have to study the existence of the directional derivatives. at 0, 0. So for that, what we'll do, we are considering one vector v, v1, v2, R2 except 0, 0. So any vector is there. Now we are going to find the means direction derivative in the direction of v. Okay. So the definitions, we recall the definitions here. The definition of direction derivative. So dvf00 will be given as limit t tends to 0 f at the point where we are calculating the direction derivative plus t along the vectors v, that is v1 v2 minus f of 0 0. So if we simplify it, so you will get it here f of t v1 t v2 minus f of 0 0 over t. So we recall the function, we recall the function here, f of xy equal y to the power 3 e to the power y x square plus 3y square. So from that we are substituting here this one from this part. So you will get it, this expression, and f of 0 0 is 0 and divided by t. So therefore if you simplify it, so you will see here t square and t to the power 3, that's will go on t, and this t and that t cancel out. So we left with this part, and then v1 square plus 3 v2 square. So since it is e to the power t v2, and when t tends to 0, so this will be 1. So therefore you will get the limit v2 to the power 3 over v1 square plus 3 v2 square. So since v1 and v2 are togetherly cannot be 0, so therefore this limit exists and we have the directional derivative. Now, the third part is that conclude that f is not differentiable at 0, 0. For that, we assume this, we'll show it by the contradiction. So we assume that f is differentiable at 0, 0. So since it is differentiable, then for any v, the directional derivative exists, and the directional derivative is related with the derivative of the vector function like this relation. So it is equal f dash 0 0 phi. Now we already calculate the directional derivative of this, and now we are going to calculate this one, and we compare them, and we'll see that what is the contradiction. So now the derivative of this can be calculated as df dx 0 0 v1 plus del f del y 0 0 at v2. Okay, so this is the relation between the derivative and the vector. So then from part B we have here that directional derivative of f00 is v2 to the power 3 v1 square plus 3 v2 square, for v is equal v1 and v2. So is equal e1 1 0, then this is equal to the partial derivative of f along the direction x, so which is equal to de1 f00. So in this case means v1 is 1, so this means v1 is equal 1 and v2 is equal 0, and if you substitute it here, so you will get it the value 0. So therefore the partial derivative at partial derivative of f with respect to x at the point 0 0 is 0. Same way, if we take e2, b is equal e2 0 1, in this case we will have here v1 is equal 0, v2 is equal 1. So again, from this relation we get it that from here we get it that the partial derivative of f with respect to y at 0, 0 is equal 1 over 3. So we got the relation here. So therefore, from this relation again, come back to this. So you will get it. Then from the previous part, we will have here v2 to the power 3 and v1 square plus 3v2 square is equal to 1 over 3 v2. So now if you simplify it, then you will get it v1 square multiply v2 is equal 0. How it is? So if you cross multiply it, you will get it 3 v2 to the power 3 is equal v1 square v2 plus this 3 v2 to the power. So this 2 cancel out and you get it here. You get it here. This implies v1 square v2 is equal 0. So now this is possible because v1 and v2 are togetherly cannot be 0. So therefore this is possible. Either v1 is or v2 is 0. Okay. Now in the case of v1 and v2 are non-zero, both are non-zero. So let's say v is equal to 1 1. Then what will happen? Then from this relation we get it. Then we have this implies, so this relation implies that 1 over 4 is equal 1 over 3, which is a contradiction, not possible. So therefore our assumptions that the function is differentiable is wrong. So we got the conclusion that function is not differentiable at 0, 0, 1. Now we move to the example 2, and here it is similar kind of the function we have. So this is the expression when xy is not equal 0, 0 and 0 when xy is equal 0, 0. Again, we have to show that f is continuous, and then we have to discuss the existence of partial derivative at 0. So let's so the first part, the continuity will prove it in the same way as in the previous example with this by showing that g and gxy tends to 0, 0 as xy tends to 0. So again, just recall the function. So function is f of xy minus f of 0, 0. It will be like this. So again, with the same logic, we can say that this is yx and this. So this is actually less than yx. So again, by the same logic as we saw in the previous, so y square over x square plus 2y square, which is less than equal half and less than 1. Okay, so we'll take this as a g. So gxy equal yx. Then we'll see that gxy is tends to 0 as xy tends to 0, 0. And from there we'll say that f is continuous at 0, 0. Okay. Now we'll see study the existence of the directional derivative at 0, 0. For that, we consider the point vector v is equal v1 v2. So for that we consider the vector v is equal v1 v2 belongs to R2 minus 0, 0. Then using the definition of the directional derivative, we will have now from the function f, we substitute here. So we'll see that here t to the power 3 and t, so it will be t to the power 4, and this is t square and there is t, so it will become t to the power 3. So it, after simplifications, you will get this form. Then this t and t to the power 4 over t to the power 3, this is t. Since t tends to 0, it will become 0. So therefore, the directional derivative is 0 along any direction. The directional derivative is 0. So therefore, the partial derivative exists and it will be 0. So for that, we will take it here that for v dv is equal 0, and in particular, if we take v is equal u1, then you will get the partial derivative with respect to x is 0, and then if you take v is equal e2, and then you will get the partial derivative with respect to y is 0. So therefore, the first order partial derivative of exists at 0, 0. So this is the conclusion. Okay, now we have an examples. Here again, we are taking the functions from R3 to R, and we are going to discuss the continuity of f. And then again, we are going to discuss the existence of the partial derivative at 0. Okay, here you have to note that we are going to discuss the continuity of f at 0, 0, 0. So it does not, like the previous question, it is not guaranteed that function is continuous or not. Okay, so we will see that here that it is a continuous or not. We want to going to discuss it here. So here we will take it with respect to the first we will discuss about the continuity. Is it continuous or not? So we took this a sequence a n is equal 1 over n, 1 over n, 1 over n on R3. And then clearly we'll see that a n tends to a0, 0, 0, 0 as n tends to infinity. So which is clear from this because 1 over n tends to 0 when n tends to infinity. So now we are checking that where f of a n is going. Is f of a n will go to f of a0 or not? So here we'll see that f of a n, which is equivalent to f of 1 over n, 1 over n, 1 over n. So now from the given functions, we have here this expression. So you will see that after simplifications, we are getting it 3 over 4. But it's given that f of 0, 0, 0 is equal 0. So therefore, this is not equal f of 0, 0, 0. So but here a naught is 0, 0, 0. So this will gives us to conclude that a n tends to a0, but f of a n does not tend to f of a0. And hence f is not continuous at 0, 0, 0. So function is not continuous. So again we consider now three component vector v1, v2, and v3. Then by definition we'll have this expression. So we substitute it and we'll see that here this is become like this. Now here t square it will go on. This t square will cancel out. So we have an expression in this form 1 over t. So which does not exist when t tends to 0. The limit does not exist. So therefore first order partial derivative of does not exist at 0, 0. Okay, now we have an interesting example here. So in this example, we have a linear transformation or linear functions from Rn to Rm, and B is a vector in Rm, and we consider a function f R3 to R. Sorry, this is Rn to R defined by f of x is equal half ax minus b whole square. Here x belongs to Rn. Now we have to show that f is differentiable and we have to find f dash x. we have to conclude that gradient of f can be written as in the matrix form with this A transpose, the matrix of linear function A, its transpose, then AX minus. In particular, if A, X and D is given, then what is the value of gradient of f? So this thing we have to calculate. So first we'll show that f is differentiable, though it is proved in module 3, but we will revisit it and we will prove it again. And then we will find the f dash x. So part B is depend on part A. So let's have the solution here. So we recall the definitions of the differentiability. So for that we will write f x plus h is equal f of x plus th plus epsilon h, absolute value of h, where t is linear and epsilon h tends to 0 as absolute value of h tends to 0 is, and for h belongs to Rn, f dash x h is equal th. So from this we will have in this case f of x plus h, which is half of mod of ax plus h minus b whole square. So this is equal half ax minus b whole square plus th plus epsilon h, absolute value of h. So we'll classify the th and epsilon h simplification. So this is equal half. So now we can write it this a plus b whole square. So this is ax minus b plus ah whole square. This is equal half ax minus b whole square plus th plus epsilon h mod h. So from this we will have here the absolute value. We will open it. So this will be half and absolute value of ax minus b whole square plus this will be ax minus b dot ah plus half ah whole square. So this is equal half ax minus b whole square plus th plus epsilon h, absolute value h. So if you compare this, you will get it. So this will cancel out with this term, and then we will get a relation here. This one will be with th and this one with epsilon h, absolute value of h. So therefore we get it here. th is equal ax minus b dot ah and epsilon h is equal half ah whole square over absolute value of h. So this we already saw linear. So this is linear, and this is tends to 0 as h tends to 0. So this is uh, already shown in some video previous lecture. So I'm not going to prove it. So just we are going to take that with this, it will be the derivative. So therefore f dash x h is equal ax minus b dot ah. Okay, so using that previous definitions, we are going to conclude that gradient of fx is equal this one. So from the previous part, so we got f dash x h is equal th, which is equal ax minus b dot ah. So we know that f dash xh is equivalent to gradient of f of x dot h. So this is equal a star ax minus b dot h, and a star is adjoint of a, okay, which is defined as ax dot y is equal x dot a star y. So using these properties, we can write it this one in this form. So therefore, by comparing, we have gradient of f of x is equal a star ax minus b. Now the matrix of is known that matrix of a star is equal A transpose. So therefore, in terms of the matrix, gradient of fx is equal A transpose, then matrix A x minus B. Okay, so now next part is if is this is the relation, then what will be the this gradient of f? So last question is the gradient of f in case of a is equal like this. So therefore we will recall from part B that gradient of f of x is equal matrix A transpose and then matrix A x minus matrix B. So A transpose in this case it will be 1, 2, 3 and then 0 minus 1, 2 and then matrix AX. So operating on 1, 0, 2 minus 1, 3, 2 operating on minus 1, 2 minus B matrix 1, 0, 2. So this is equal 1, 2, 3, 0 minus 1, 2 and then simplify it. So what it will be, this is minus 1. This is minus 2, so minus 4. It's minus 3 plus 4, so which is 1. Minus 1, 0, 2. So this is equal 1, 2, 3, 0, minus 1, 2. And then if we simplify it, so this will become minus 2, minus 4, minus 1. Multiply it. You will get it here. Minus 2, minus 8, and minus 3. And this one will be 0 plus 4 minus 2. This is equal minus 13, and this is 2. So the gradient of f at the point x is equal minus 13 over minus 13, 2. So therefore, gradient of f at minus 1, 2 is equal minus 13